Galileo certainly was the most problem-plagued interplanetary project ever.
We had this spacecraft that we couldn't touch. It was so far away, and it had such a huge hardware problem.
We had problems with trajectory. We had anomalies in flight that we had to work through. We had this high-gain antenna failure. We had the tape recorder. All throughout, we had one adversity after another.
We knew that at every encounter, something was going to happen.
We were scared. We were scared of that radiation environment. We were scared that the spacecraft would undergo multiple faults and just would never come back.
It's sort of like when you go through fire, you come out strong.
It brought the team together, though. It brought out the best in us. There was a heroic effort to salvage Galileo. We did remote telesurgery from 500 million miles away.
And so for me, it's just this story of hope and ingenuity.
We don't have a can-do attitude. We have a will-do attitude, and we will find a way to get this beast to work.
By the late 1980s, an armada of NASA spacecraft was sailing across the solar system. Two of the most distant were the Voyagers. Their reconnaissance of the outer planets had set the stage for the first orbiting missions to Jupiter and Saturn that would also be built and flown by NASA's Jet Propulsion Laboratory in Pasadena, California. The first to fly was Galileo, destined for Jupiter. If any spacecraft could be said to have had 9 lives, it was this mission. More than once, Galileo barely survived the budget axe. After the loss of the Space Shuttle Challenger, Galileo was stowed away, mothballed for 3.5 years. The mission endured a court battle and protests over Galileo's 50 pounds of plutonium carried on board as its power source.
We have a goal for main engine start.
Another challenge was NASA's policy requiring Galileo to be deployed from the shuttle.
The spacecraft is stable. Galileo is on its way to another world. It's in the hands of the best flight controllers in this world. Fly safe.
Galileo's post-shuttle deployment rocket lacked the power to travel to Jupiter directly. To gain enough acceleration, JPL navigators cleverly charted out a gravity assist at Venus and 2 by Earth. That meant that Galileo would have to start off headed in the opposite direction from its intended destination. To reach the giant planet in this way would take 6 years. The 2 Voyager brief encounters with the planet's innermost moons had already revealed a surprising amount of diversity that scientists were eager to explore further. And then there was Jupiter itself. Understanding how it had formed might hold clues as to how the entire solar system came into being. But after the first Earth flyby, Galileo had its first crisis. The spacecraft's main antenna had refused to deploy, putting the entire mission in jeopardy.
We have overwhelming evidence that the flight antenna is in this configuration. We had 3 stuck ribs on the one side that we just couldn't get out of the sockets.
That was a big deal. It looked like things were over. I mean, we're going down from a 10-foot antenna to something the size of a coffee can, And we got no idea how we can send down the data that we wanted to send down until we started working the problem.
First, it's try it again, try it harder, hit it a few times, and then people started going with the wild ideas of, hey, let's turn it away from the sun and cool it down. And let's put the sun right on the antenna and see if we can warm it up. So we had years of doing these warming and cooling turns and trying out things.
Nothing worked. In desperation, there began a search for a different kind of solution, one based not on hardware, but software.
The mainstream activity at that point were people who were concerned with, okay, the antenna didn't open, let's make it open. I had a different view of this. Everything on the spacecraft works except for the antenna. Is there some way we can do this mission without that antenna? Because everything else is fine. And we just started brainstorming. Now, I have to understand Galileo was old technology when it launches. The microprocessors on board Galileo were of the same vintage that were used in the very first generation arcade games like Pong. We essentially completely reprogrammed the spacecraft. That put on board the new error-correcting codes, the data compression algorithm, something we call packet telemetry, optimized receivers, arrayed antennas. We allowed the spacecraft to change the data rate that it would transmit with as a function of time.
This software transformation was likened to a complete brain transplant, performed at a distance of 400 million miles.
So what we'll do is we'll load these extended memories first, and then we'll switch over to operate on them. Again, I'm simplifying a little bit. Then we'll copy.
It wasn't a solution, it was many solutions. I mean, there were solutions in the spacecraft software, there were solutions in the instrument software.
Then we'll copy into the standard memory the new flight software, and then we'll...
It was an incredible learning experience for me to go through this process, to see how people can be so responsive and creative in the face of a serious anomaly.
We are working both of these issues in all of our...
The solution required using the spacecraft's less powerful low-gain antenna that was working to slowly transmit data. Data that first had to be stored on what was even then old technology. A reel-to-reel recorder. All hope rested on these thin layers of magnetic tape.
All of the team, the family, never quit. It was very difficult to get Galileo going, and there could have been a lot of infighting. Well, if we can't get all of this, I'm going to get my piece of that. But everybody hung together, they didn't quit, and it worked.
The antenna crisis, and others that would follow, brought the Galileo team together in a way that made them feel like a family.
The antenna opener, or AO as the engineers called it, was rejected early on in the project's history because of its...
And believing it better to laugh than cry, they found a way in private to make light of their travails.
One of our prime targets, of course, was management. And it was a way of letting off steam and, sort of cementing personal relationships throughout by exaggerating a little bit.
I'm here with Galileo project manager, who's reporting on plans for cold turn number 23. Sir, could you give us your assessment of the chances you'll get the antenna open this time?
This time we're sure that the chances are pretty good that we think we know, probabilistically at least, that it's not expected that we won't fail to better understand the problem successfully. Now let me show you.
Thank you. Thank you, sir. Now let's hear from our spacecraft directly.
All of us would contribute to writing songs, and the reason it was so important to us is because it was very cathartic to sit there and, figure out how to make our struggles into, some funny song parody.
Well, bless my soul, what's wrong with me? It's three of my ribs, just a can't pull free. The bracket just got a little bit snug on them pins. I'm all hung up.
And so we ended up calling ourselves the Galileo Not Ready for Real-Time Players.
I flew past Earth and it felt so fine. Better than a ride in a bumpy truck and pins.
It really was a great stress reliever because we made fun of everybody and everything.
Talk like that don't ease my mind. Gonna get some sun where the sun don't shine.
Our number one goal was to be as funny as we possibly could. Musicality was really a tertiary concern.
Despite Galileo's lack of a main antenna, the spacecraft was already making science history. The initial flyby of Earth also provided the first global portrait of our planet in motion.
So, after the first Earth gravity assist, we took an image with our camera every minute for 24 hours so we could make a first ever color movie of the Earth making a full rotation on its axis.
Images of the backside of our moon confirmed the presence of an enormous impact basin, a discovery that hinted of surprises to come. Next came the first ever encounter with an asteroid.
We don't know what an asteroid looks like. We have a lot of guesses. A lot of them are probably wrong. So they were interesting bodies we didn't know much about, and we were flying right through there. Now, this scared the heck out of the engineers. Through the asteroid belt, that's got to be lots of dust there, and you're going to run into things. It turns out the asteroid belt in between where the asteroids are is fairly clean. But right around an asteroid where you want to fly if it's interesting, the asteroid has some gravity, and you might have a little dust cloud hanging around it.
The worry was real, for colliding with even a small particle might cause serious damage to the spacecraft. Galileo was kept a safe distance of 1,000 miles away as it flew by asteroid Gaspra and gave the world the first ever image of an asteroid. Next came the second flyby of Earth, followed by another asteroid encounter that came close to being called off.
As we were approaching Ida, I had the occasion to be on the graveyard shift, and as soon as I got into my seat, one of the temperature monitors went into alarms on one of the science instruments. Didn't know why. So I called Bill O'Neill, who came in, and I'll always remember this. He sat down to the conference room table and pulled out a jar of instant coffee and a bottle of Pepto-Bismol.
The temperature alarm was solved. But next, Galileo's inertial pointing mode, used to keep the spacecraft oriented in the right direction, malfunctioned. Not understanding the reason why, some team members saw more risk than benefit in recording measurements during the flyby. But not everyone.
We didn't know what the problem was, but we knew that we could do the flyby. We could still point the scan platform and all the instruments using just the star tracker. And the attitude control people are like, come on, we can do this.
Asteroid Ida turned out to be twice as large as Gaspra, stretching over 30 miles in length and estimated to be 1 billion years old. And scientists were delighted to discover a new first. Circling the asteroid was its own tiny moon. After leaving the asteroid belt behind, Galileo took part in an experiment to detect gravitational waves, ripples in the fabric of space-time predicted by Einstein. Nothing was seen, But the elusive waves would turn out to be very real when they were detected 21 years later. Next, out of the blue came an extraordinary opportunity. Because of its position, Galileo would have the only ringside seat to directly witness fragments of a comet colliding with Jupiter.
This is a totally new event. It's the first time in the history of civilization we are seeing an impact of a comet into a planet. The importance of the Galileo mission, you just can't say too much about it. It is the only spacecraft that both has an operating camera and that is going to be able to see the impacts directly.
The comet, originally a mile wide, was torn into pieces by the force of Jupiter's gravity. And now all those fragments were about to slam into the gas giant in a series of spectacular explosions. Over the course of 6 days, the fragments, one after another, plowed into Jupiter's southern hemisphere, exploding into massive fireballs, rising upwards more than 1,000 miles. The energy of one fragment alone was the equivalent of 6 million megatons of TNT, hundreds of times more powerful than the combined energy of all of the world's nuclear weapons.
My first thought was disbelief. This was such a complicated process. I thought the chances of actually capturing the right moment with enough information to actually record the energy coming from these things wasn't all that high. And I was just amazed at all this complicated planning and jiggling of times and this, that, and the other, and the things that had to go on to get the data back had actually worked. So I was just amazed.
Galileo's images were key to determining the force of the collisions, while the aftermath of the impacts was captured by the Hubble Space Telescope and Earth-based observatories. The Hubble images revealed vast dark blotches stretching across thousands of miles. It was a sobering reminder of the kind of cataclysmic violence that occurred during the early formation of the solar system, and that is still possible in our own time. Galileo was also carrying a passenger, a probe designed by NASA's Ames Research Center and built by Hughes Aircraft. The probe was designed to separate from the mothership 5 months before Galileo's arrival at Jupiter. It would then free fall for 50 million miles on what would have to be a precise and no second chance trajectory to reach Jupiter. If all went well with the navigation, the probe would then slam into the planet at over 100,000 miles per hour. The highest impact speed ever attempted by a human-made object. The angle of the entry had to be near perfect also. Too steep and the probe would be incinerated. Too shallow, it would bounce off Jupiter's atmosphere like a stone skipping across a cosmic pond. 2 minutes into descent, the probe's speed would be reduced to just 1,000 miles per hour. Slow enough for a parachute to deploy. From this point on, the probe would attempt to determine Jupiter's chemical makeup, measure the planet's temperatures, winds, and atmospheric pressures, and listen for sounds of lightning. An hour later, having descended just 400 miles into an atmosphere 3,000 miles deep, the probe would be vaporized.
This is the first time we've ever gone and directly sampled the atmosphere of one of the outer gas giant planets. So the sort of information that we get from this probe mission is unprecedented. This is the most difficult atmospheric entry that's ever been attempted.
the release went off as planned. A set of springs gently pushed the probe away and towards Jupiter in the far distance. Whether on the right trajectory or not, no one would know until arrival day. Nor would there be any information about the probe's health. To save its battery, the probe would have to coast in deep sleep and radio silence. An internal timer would awaken the probe just before its jarring encounter. Despite the uncertainties, rather than fret on the eve of release, friends, family, and mission members gathered again in JPL's auditorium to learn the latest on the mission.
Okay, good evening. We're going to start the program now. I hope you guys in the back.
And to hear, as was by now the tradition, from the not ready for real-time players. Though still millions of miles away, Jupiter was already making its presence known. Galileo found itself plowing through an interplanetary dust storm. For weeks, the spacecraft was bombarded by thousands of electrically charged particles scientists thought must be coming from somewhere in the Jovian system. 2 months before arrival, Jupiter could be seen in the far distance, close enough for Galileo to take pictures of the planet to share with the world. As planned, the images were stored on the reel-to-reel tape recorder, but after sending a command to begin playback, the Galileo team was shocked to discover that the tape recorder had been stuck in rewind for 15 hours.
It was one of the darkest days on the project. There were resumes flying off the printers, and we just thought the mission's over. We couldn't get one picture back from Jupiter without a high-gain antenna and without a working tape recorder.
When we had built our primary mission now on this tape recorder, that had to be the low point. It was within a day or so that we determined that we hadn't, in fact, broken the tape, and we probably could recover it. And I think it was about a week before we actually moved it. But what a relief that was. Of course, we're delighted that the tape recorder is not broken. What we don't know is just how operable it is.
The engineers cleverly figured out that the lubricant on the tape may have just gotten sort of old and sticky, and if they, as the tape recorder is running forward, once it stopped, it would get sticky and it wouldn't be able to go forward again. But if they backed it up a little bit, they could then get it going again forward. So we had to redesign the way we were laying down our data on the tape, and we had to allow for that backup and forward motion. So we had a lot of challenges, but we managed to get through them.
Leslie Tampari joined the mission as a graduate student, pursuing a PhD about Jupiter's inner moon, Io. Because of Io's intense radiation, there would be only one chance to collect data there during the prime mission. But the tape recorder crisis put an end to those plans.
We must avoid any unnecessary use of that tape recorder until we record the probe data, because there's only one chance to do that. There's never another chance to get probe data after this essentially suicide mission of the probe into Jupiter. I made that decision without having a meeting of the project science group and asking them all for their input. Well, these were tough times, and the clock was running. And I didn't need a lot of discussion and a lot of their input, because the buck stops here, and this is what we're going to do.
So as a result of that, I lost my PhD thesis. And so then I had to start over from scratch.
Tampari would go on to earn her PhD, though the topic would be about Mars. Her experience was one more example of how engineers, scientists, and even a graduate student would have to adjust to Galileo's unexpected, but certain to occur, twists and turns. Jupiter is immense, a world large enough to contain more than 1,000 Earths. Yet it has the shortest day of all the planets, just 10 hours. This extreme rotation speed helps to explain Jupiter's complex and ever-moving tapestry of cloud bands and giant storms, as well as the planet's deadly radiation, a place where not even machines can survive for long.
We don't ever experience that here on Earth, except as the result of like a nuclear weapons explosion or a nuclear meltdown. It's created because particles come off of Io and get ionized and spun up by Jupiter's magnetic field, and so these very, very fast-moving ionized particles constitute radiation, and they're incredibly destructive to living tissue. They go through your body like a bullet. They're very hard on electronics, as we found out.
Galileo was now on final approach after a journey of 2.5 billion miles. To be captured into orbit, the spacecraft would be flying close to the planet and Io, taking on the heaviest dose of radiation expected during the entire mission. A great worry was knowing that energized particles might penetrate the spacecraft, causing any number of computer sequences to crash. All of the science data from the probe might be lost, or the main engine needed to go into orbit might not fire.
This was a risky thing. This is one of the riskiest things that Galileo was going to do. So I think people were, in some cases, almost terrified.
And the greatest stress, of course, as we were planning for arrival at Jupiter was the new software going to get there? Was it going to work? It was very long nights staying up, staying at work until 3 in the morning or whatever, running tests in the test bed, and just, not a lot of sleep. And everything was riding on this. I mean, it all had to work.
December 7th, 1995 was arrival day. At JPL, the press, accustomed to Voyager's encounters, was out in full force. They would be busy reporting on whether the probe survived atmospheric entry, and if so, would Galileo be successful in capturing the probe's precious data? And then, would the main engine fire to put the spacecraft into orbit? One critical event would follow another, and yet, while this would be the mission's busiest day, there was actually very little anyone could do.
On the day itself, it's all pre-canned, it's loaded in spacecraft memory. There's nothing we can do about it. If we find out that something is not going to work, it's going to be 45 minutes getting the signal from the spacecraft saying help back to the Earth, us looking at that data, scratching our heads, figuring out what's wrong, figuring out what to do to correct it, and then it would be another 45 minutes getting a signal back to the spacecraft, and an hour and a half later, it's too late to do anything. There was nothing we could do except twiddle our thumbs and sweat and chew antacids.
And unlike Voyager encounters, there would be no images to see in real time. The most the overflow crowd of guests could expect would be to know they would be the first to hear of Galileo's success or failure.
Everybody really wanted to find out as soon as possible whether the probe had worked. The mission design people actually figured out a way to get 1 bit back. We were all waiting for 1 ping.
The Galileo orbiter is a mere 1.5 Jupiter radii away from the planet and has just reached its closest approach.
Galileo was kind of an odd event in that we were used to this giant picture show with Voyager,
And because of the antenna problems we had on Galileo, we knew it was going to be very, very restricted. We had all these people there to host, and we had to kind of fill in, give them something. Okay, anything going on at the MSA yet? We can look at that again. They're still very, very patient. And hopefully later on in the day, people will be cheering, but maybe not. We had people in a fishbowl, basically, or an aquarium. There was a glass window, and they were enclosed in this box. And in those days, we had no live audio. We'd actually call them up on the phone, and they talked to us over a phone. It was a really kind of a crazy way to do that. We're listening, and we're watching, and
there's the man.
I'm
Come
sweating.
On, Bill. Do your stuff.
We put our management in a room where they weren't supposed to be bugging us. I see the data come down. Some of us are like, yes, this looks good, but don't react. We're very much told, don't react on camera, you know.
Right, right.
It's just the same.
Oh, there's applause.
Confirmed 693.
All right. All right, we got it. All right, we have confirmation of telemetry lock. Everybody's... Wow, oh, this is great.
I've never seen so much yelling and screaming over just one bit of data.
The probe made it. The probe survived its fiery entry into Jupiter's atmosphere. One enormous thing down today, and one more to go. Hi, Bill. Give us a wave, and what's happening?
We're having a great time here. I want to welcome everyone to the guest operations about to witness with us the momentous event of the first spacecraft going into orbit about Jupiter. And we are just ecstatic already because we have confirmed that indeed the probe was successful. We're just about completed with the spin-up maneuver preparatory to lighting the main engine.
It's a 49-minute burn, but I mean, if we burned for 40 minutes, would we still be happy?
There's not a lot of leeway, and if we burned for 40 minutes and stopped, we wouldn't be very happy. The consequences of it not working right were catastrophic to the mission. If we didn't get the burn off completed within just about exactly the right time, then we would have just gone flying on by Jupiter and out into a solar orbit and been out there forever and no Galileo mission.
Another hour of nervous watching and waiting would have to go by before it would be known whether Galileo would become Jupiter's first orbiting spacecraft. The time was used to hear from one of the mission's most influential supporters.
Carl, welcome.
Thank you. Happy to be here.
Another encounter?
Another encounter.
Another notch in your belt.
Well, another great encounter. And I'm just so glad that after all these perils of Pauline that the entry probe entered, that the tape recorder is recording, that the burn to achieve orbital insertion is burning. All that's just terrific good news.
And he was a real mover and shaker in Washington and in the science community and in many, many communities to make Galileo happen.
We'll have actual data, hands-on data. I mean, it's really epical in the history of planetary exploration. The whole mission is.
Let's go around to the lab and see how people are reacting, waiting for the news. This is Von Karman Auditorium, and people are patiently waiting for the engine cutoff. Again, the final moment. We got something. We got an engine cutoff.
The day of arrival, all the events of the day of arrival, all rolled into one. I mean, that was the absolute ultimate. That was spectacular, that everything worked properly.
And it is my distinct pleasure to declare not only are we in orbit, but we're in a very good orbit.
Galileo certainly was the most problem-plagued interplanetary project ever. And we dealt with them all. And I guess we got our reward because on the day of arrival, everything clicked.
A lot of the questions we get are, is Galileo going to search for life? What are the prospects of life in the Jovian system? And maybe you can give us a little bit of a perspective on that.
Where might we look? The possible subsurface ocean of Europa is a very interesting environment. If there's liquid water, while we're not going to send some part of Galileo down subsurface, there's a very good chance of elucidating much better our knowledge of what's happening on Europa.
The bittersweet part of that is that Carl passed away about a year later. And that was one of the last times, it was the last time, I guess, he was at JPL.
Galileo is going to do wonders. And in just this last few months, there has been a credible announcement of a discovery of another Jupiter-like planet around a very different star, 51 Pegasi.
That's right.
And so what we're doing here is not just studying the Jupiter in our system, but in a certain sense, the whole category of Jupiters, of which, if the 51 Pegasi discovery is right, there must be an enormous number around nearby stars. So there's a whole new genre, category of things to explore. It's an epochal time in the history of human exploration.
Soon after orbit insertion, Galileo began transmitting back probe data that scientists had long hoped to have.
Now, why do we want to go to Jupiter? Because it tells us how the sun and planets formed from the early solar nebula, the original gas and dust cloud from which all the planets formed. Probably you all know that Jupiter is the largest planet in the solar system. The analogy I always like to make is that if you took a tomato, we sort of sampled the skin of the tomato, but we learned some very important things.
The findings were, as described in the NASA press release, startling, as they ran counter and at times contradicted some long-held assumptions.
And this arrow points to the probe entry site.
Instead of a distinct three-tiered cloud structure, there was only one. Temperatures were higher than projected, and winds were clocked at twice the anticipated speed. An expected swarm of super bolts of lightning went missing, except for a single horizontal line in an upper latitude of the planet.
There was almost no lightning occurring down anywhere else on the planet.
Nor did Jupiter's chemical composition match that of the Sun, as was assumed.
But what we found out from Galileo is that's not really the case.
The most puzzling finding, though, was the lack of H2O.
So that's been a major surprise, that the amount of water is so depleted. And that's really hard to understand. As it turned out, what happened is we probably went down into a feature that looks very much like this. This is probably a hole in the upper cloud layers of Jupiter. And what we're looking at here is what's called, quote, a hotspot. The clouds that we experienced there are not typical of Jupiter as a planet. That was sort of a minus.
The probe had descended through an area lacking in clouds. Scientists called it a meteorological anomaly, a way of saying the probe had, by chance, hit a dry hole, representing just 1% of Jupiter's atmospheric possibilities. It led one scientist to quip, "We need more probes." Meanwhile, Galileo was in the midst of its first and longest orbit of the entire mission. Up next was the first encounter with Ganymede. Ganymede is the largest moon in the solar system. If it circled the Sun instead of Jupiter, we would call it a planet. The Voyagers had shown it to be a world of rock and ice with a surface hinting of a complex and ancient tectonic history. Not much more was known.
I'm happy to report that at this time, all engineering subsystems on the spacecraft are nominal and operating as expected. To give you
It was so interesting because it was my first flight project.
Galileo is currently 27,300 kilometers from Ganymede.
The atmosphere was just intense, and I loved it, and I thought it was always like this.
So all is well, and we're looking forward to some great science data. Thank you.
We had some major surprises almost off the bat. We got images of the surface at high resolution. We found that it had distinctly different types of terrain, some of it very young geologically with very few craters on it, but lots of ridges and cracks on it. From the beginning, one of its objectives was to look for magnetic fields in these moons. The theory says, well, probably, you know, it's not a huge rocky object, probably not hot inside, so it's probably not producing a hot molten core like the Earth to produce a dynamo effect. Ganymede had a magnetic field.
Ganymede is the only moon in the solar system known to have a magnetosphere, and measurements of it raised a tantalizing possibility: a liquid ocean under Ganymede's crust. Today, the question is not whether, but how much water lies beneath its surface. The flyby of Ganymede further reduced the length of Galileo's follow-on orbits. It was one element in a vast web of trajectories designed by JPL navigators. Time and again, they charted plots that would send Galileo skimming daringly close to the surface of a moon. The force of its gravity would be used to hurl the spacecraft towards its next intended target, all with exquisite precision. Rightly proud of their accomplishments, these mathematical wizards were known to literally dress for the part. It was another moment of levity employed to cope with the seriousness of their task. From now on, encounters would be occurring far faster, one after the other, leaving the entire team with little time to regroup. On the third orbit, the main target was Callisto. Here may be the oldest landscape in the solar system, a surface 4 billion years old and littered with scars left by tens of thousands of impacts.
Callisto, very ancient surface, and once again we had a surprise. It wasn't just ancient and cratered, the whole surface seemed to be kind of buried in dark rubble, and no evidence of a magnetic field there either.
The Callisto flyby also marked the mission's first use of a technique of lashing together an intercontinental network of giant antennas. Listening in this way, the amount of data that could be captured was increased by a factor of 10.
When your antenna has gone from a pipe to a little straw, they were constantly thinking of new ways to do things, and it rippled into every part of the operations. And that's when I first learned that when things go wrong, you also have an opportunity to fix them.
And things did continue to go wrong, often causing Galileo to go into safing, a pre-programmed response when the spacecraft senses something is amiss. The spacecraft automatically shuts down all non-essential functions and then phones home, asking ground controllers for help.
Galileo seemed to be in safing all the time. One of the big challenges there, it was a spun-despun spacecraft. So the top half spun at 3 revolutions per minute and the bottom half with the cameras was fixed. Trying to communicate from the spun section to the despun section, we had to go across a slip ring, which is kind of like a steel wool electric connection. And we found that the slip ring generated debris which caused shorts all the time.
The team could also count on safings due to radiation.
Almost the only way you can explore these inner moons in a highly toxic radiation environment, you have to limit your exposure. Go in and come back out. Go in and come back out.
Each new orbit added to the accumulation of radiation exposure. Just how much the spacecraft could withstand before its electronics would fry and cease to work, no one knew. And where scientists most wanted to go was in close to Jupiter, to places like Io, where radiation was most dangerous. but the risk was worth it, for what Galileo witnessed at Io is almost hard to imagine. Here is a place where hundreds of volcanoes are constantly erupting. These fireworks are due to Io's location. It is caught in a tug-of-war between Jupiter, Europa, and Ganymede. This back-and-forth gravitational pull distorts Io's shape, causing extreme heating in the moon's interior. Unable to contain itself, Io erupts with massive walls of lava and plumes shooting upwards into space.
We flew by Io, and we were expecting to fly by one volcanic plume from the volcano Chvasta that we knew about from a previous orbit. And we realized that the next flyby, the spacecraft was going to go through the edges of that plume. And what we didn't know was that before that next flyby, another volcano erupted, had a gigantic plume 500 kilometers high. And Galileo went right through it. So with Io, it was difficult to plan because you might plan to avoid one volcanic plume, but you didn't know you were going to fly through another one that had never been seen before.
Jupiter is surrounded by a constellation of 79 known moons. Of them all, Europa has been the most intriguing, dating back to the time when Voyager 1 took this image from 1.5 million miles away in 1979. Here appeared to be an unusually smooth and young surface, devoid of craters. Voyager 2 traveled closer and was able to make out a patchwork of crisscrossing linear structures. Galileo's images would be even more detailed and far more revealing.
Europa was, I think, anybody's superstar of the Galileo mission. Just the first couple of encounters with Europa with Galileo just kind of blew us away.
We found a region where it looked like pieces had broken off, like an iceberg, and drifts in a watery body and twists. People who study the Arctic recognize some of these floating patterns as clearly an area where the underneath was liquid.
Some of these rafts of ice were the size of cities. There were also indications of ice flows and the possibility that water had even flowed on the surface, all pointing to the existence of a subsurface ocean.
The magnetometer came through with the final piece of data that really nailed the ocean model. It was responding exactly as if you had a big shell of salty water.
Europa, about the size of our own moon, may hold more salty water than all of Earth's oceans combined. What had once been only speculation was now deemed worthy of serious consideration. Is Europa a place where life could, or does, exist? Ironically, the question was the beginning of Galileo's demise.
So we came up with the plan to basically ram it into Jupiter and sterilize it with the energy of the impact. It's something that I still second-guess myself about, was there another way? But the problem was, the vehicle was getting old. It was having failures, and we couldn't wait too long or we lose the opportunity. So we tried to figure out the perfect time to do it. And I guess we may have been a little conservative, but not by much.
With its fuel tank nearly empty, and knowing the spacecraft could possibly have on board microscopic life from Earth, Galileo was put on a collision course with Jupiter to eliminate any chance of colliding with Europa.
Hello, everyone. We'd like to welcome you to live NASA TV coverage of Galileo's grand finale. With me right now is Claudia Alexander. She is the 7th and final program manager of Galileo. We have a display right now that can actually explain what's taking place. Can you go do that right now and explain?
Yes, what we want to know, of course, is what's happening with the spacecraft. What's going on? You'll see that we've passed most of the major moons. We've passed Io, and we have passed the moons Phoebe, and we're actually going past the moon Amalthea at this moment. And believe it or not, folks, we are still collecting science data, and I am absolutely thrilled about that. We're still clicking along, and we're still doing it. So, you know, go Galileo, go.
It was very sad. Trying to keep this spacecraft alive, day after day after day, doing everything we can to keep it going and keep it going. And now we know that we have deliberately told it to take a dive into Jupiter and evaporate and never be seen again. But it's also very joyful because we know we can look back at an amazing mission.
Among Galileo's firsts was delivering a probe to measure Jupiter's atmosphere. Galileo was also the first to conduct long-term observations of the Jovian system, finding evidence of subsurface water on Europa, Ganymede, and Callisto, while adding new knowledge about Io, the most volcanically active place in the solar system. Galileo was also the first to fly by an asteroid, the first to discover a moon of an asteroid, and the first to see a comet hit a planet. Galileo's legacy, though, is as much about endurance as science. It is a story of a spacecraft and its team of engineers and scientists who faced adversities and overcame them through stubborn determination and extraordinary dedication.
We all still talk about Galileo with a smile on our face. And I think of it as, you know, it's like your first love, you know, and you know, I use your first love and your first child, and there's just sense of all of these great people.
When you think about the spacecraft itself, it might be tempting to think of the pieces of metal that are its constituent parts. But for me, the ideas that it has given us will remain, and follow-up ideas, what we want to do now that we know so much from the mission, will be its legacy. So for me, the mission is much more than steel and titanium.
So the final moments, there's a small group of us sitting in the main control room at JPL here and watching the radio signal as it finally vanishes. There were a couple of people who were crying. I remember Claudia Alexander, who is not with us anymore, was standing right there, and she just reached over and gave me a great big hug.
We are now less than a minute away from the end of mission. They are counting down here in space flight operations. The final moment in the great mission, Galileo is gone.
Mixed emotions. Sad to know that we won't be getting back together much as a project and seeing the people again, because these people have become our family. We care about each other. We've seen marriages and children and divorces and deaths. These people are incredibly important to you. And it's sad that you won't be sharing these experiences anymore with them and getting together and writing clever songs to poke fun at the next thing that comes along.
Good afternoon, friends and colleagues, and welcome to the first annual farewell performance of the Not Ready for Real-Time Players.
In Von Karman, we got up there, and I know I broke down in the middle of that. I think I'm starting to do that now, just remembering it.